Hi everybody, and thank you for watching this video. This is an exam prep video, and at this point before watching the video, you should have attempted the practice exam on your own. And I do recommend trying it under exam settings. That means sitting in a quiet area, working on it, trying to do it within like an hour and a half or so. Now, that being said, this exam is harder, or the exam prep is harder than the exam itself, and that's by design. It's meant to get you really thinking about the ideas that are present. If you have not done the exam prep yet, the sample exam, stop the video and do it, and then come back and watch through this sort of solutions type video afterwards. Okay, so jumping into question one, right? We're shown this graph of force versus distance, and we're asked something about the work done by this force. Now, there are a couple of ways we can deal with work, but the most important thing to understand here is that work is equal to the integral of force dx. And why is that important? Well, that's important because the integral of force dx, well, that just is equal to the area under the curve of force and displacement. So you find the area under the curve and you have the work done on this object. Once you have that work done, and I'm going to erase what I just drew on the graph. Once you have that work done, well, you could do things like say work is equal to your change in kinetic energy. This is the work kinetic energy theorem, and is incredibly powerful, right? This problem doesn't ask us to use it. We're just finding work, but it can be used to figure out things like changes in kinetic energy, which tells you about changes in speed. So we go back and we say, okay, well, how do I find the area under the curve? And that's purely a geometric problem. We can envision this curve of being made up of separate shapes, and I'm going to outline first this blue shape. That blue shape is a rectangle. We know how to find the area of a rectangle. It's base times height. We look at this and we see also a green triangle right here. And we know the area of a triangle is 1/2 base times height. And we also have down here a second triangle. I'm outlining in orange. And again, 1/2 base times height. But here our height is -4. That's going to be important. We keep that in mind. But the total area under the curve, well, that's just going to be the summation of these three different parts. So I'm going to label these. Part 1, 2, and 3. Shape 1, 2, and 3. We're going to find the areas of each of these. Okay. Shape 1. The work done in area 1, the triangle, is going to be 1/2 the base, and the base here, well, it starts at 1 second, or 1 meter, sorry, and it ends at 4 meters, so that means the base is 3 meters. So 1/2 base times height. The height of this triangle goes from 1 to 4. 1 to 4, well, that's a change in 3 newtons. So what is the work done here? Well, it's going to be 6 Newton meters, or I did my math wrong there. My apologies. Not 6 Newton meters. 3 times 3 is 9. Half of 9 is 4.5 Newton meters. We can also write this as 4.5 joules, right? The unit of energy is a joule. And then you just repeat the process. Well, what is it for work done in section 2? Section 2 is a rectangle with height of 1 Newton and a width of 4 meters. So the work done there is going to be 4 Newton meters, or 4 joules. And then we look at the final area, the triangle that I outlined here in orange, and we say, well, that's a triangle. The area is going to be 1/2 the base. The base is 2 meters here, starting from 4, ending at 6. So our base is 2 meters and our height is -4, nope, forgot my units, -4 newtons. So in area 3, we have the work done is going to be -4 joules. So does that mean the total work done from 0 meters to 6 meters is going to be 4.5 joules? We look at this and we say, okay, well, we have the work done from 0 to 6 meters. But hold on, because I wasn't careful. And I hope some of you are screaming at your screens because there's an important thing I missed here. Oh no, it's not asking for the work done from 0 to 6 meters. We have to keep in mind that the question always asks for something specific, and we need to know what the question asks for. Here it doesn't ask for the work done over the entire curve. Rather, it asks from starting at 1 meter, ending at 5 meter. What is the work done to undergo that path? Well, it's going to be comprised of a couple of different shapes here. We have a rectangle again. We have a triangle. And we have a second triangle, although a shorter triangle. So we find the area of that for the actual answer to that question. That's something I will leave up to the viewer. We go on to the second question. The second question asks about conservation of energy. Conservation of energy is important because your initial energy must always equal your final energy with the addition of any outside work that is being done. So we'll say work plus energy initial equals energy final. Well, kind of. I'm actually going to erase that. I'm going to be more specific. Energy initial plus work done by non-conservative forces is equal to your final energy. This is how we best phrase it. Why do we do that? We do that because our conservative forces, in this case the force of gravity, will be counted as a potential energy. So we write this whole thing out as being your initial energy, half mv squared kinetic energy, plus mg times initial height, plus the work done by any non-conservative, and in this case that means non-gravitational forces, must equal the final energy, 1/2 mv final squared plus mgh final. We look at this and we say, well, initially, we can define our initial height to be 0, meaning our initial potential energy goes to 0. And we look at the rest and we say, well, there's not much else I can simplify here. But the good news is we can make a few numerical computations, because we actually know our mass and our initial velocity, right? 12 meters per second. We know our mass and our final height, 2.5 meters. We don't know our final velocity. And our work, well, our work is interesting because our work, well, we can't calculate it. How do we calculate it? The work done here is going to be by friction. Friction is a non-conservative force, so it does non-conservative work. And we can define that work done by friction to be the force of friction, in this case kinetic friction, multiplied by the normal force. And the work is force times a distance that we travel. So that is going to be this distance here. I'll call that delta x. Not using x to mean horizontal, just meaning delta x is the direction of travel. And we look at this and we say, well, we don't know what delta x is, right? And we don't know what the kinetic friction force is. But we can find both of those, right? Because the kinetic friction force is equal to coefficient of friction times the normal force. And on an inclined plane, the normal force is going to equal mg times the cosine of the angle of the incline. In this case, that would be 35 degrees. We know mg is 9.8, theta is 35, mu is 0.8, so we have all of those values. Then we take a look at this and we say, okay, well, that's a right triangle. I know the height is 2.5 meters, and I know the angle is 35 degrees. So that means that the hypotenuse and the opposite leg are related to each other by those trig functions. So we use sine of 30 degrees is equal to opposite 2.5 meters over the hypotenuse delta x. We can solve this for delta x. We can solve this for the kinetic friction force, meaning we can solve this to get the work done, find a number from that work done. Take that number, plug it in up here, and you are able to then solve this equation for the final velocity. Again, this is something I am going to leave up to you to do at home, but this is the steps to go there. Now, what was the important step? What was the main important thing here? The big thing is understanding this conservation of energy law, this idea that energy must be conserved, and any energy that is being removed or put into the system is counted as work, the work done by non-conservative forces. Okay, so second problem, conservation of energy, just saying initial energy plus work is equal to final energy. It is crucial here, it is important that you do not use gravitational force in your work. It must be work done by non-conservative forces. And the reason why is because we're counting the gravitational force in this potential energy term. We're counting for the gravitational force in the potential energy term, meaning if we included work as gravity, work done by gravity as well, we would be double counting that force. And we would end up with something that would have twice as much gravity acting on, and obviously that isn't happening. So you want to make sure to exclude gravity and exclude springs from any sort of work that is done. All right, we move on to the third problem. And the third problem is all about the idea of impulse and momentum, and specifically utilizing the idea that impulse is equal to the change in momentum delta P. Well, impulse can be found as the average force multiplied by the time that that force is being applied for. And of course, delta P, well, that's going to be your final momentum minus your initial momentum. So that means you find your change in momentum, and if you know your time, well, then you can find the average force. So we read through the problem and we say, okay, well, we have the mass. Okay, maybe that's going to be useful. We have a speed. Okay, mass and speed. Well, I know momentum is mass times velocity. And I have speed 7 meters per second moving horizontally. That's the direction. So we have the velocity. Wonderful. We have enough to calculate the momentum before the impact, before it collides with the nail. And then after it comes to rest. So that tells me that my final momentum must equal 0. It comes to rest. So this means I have enough information to find my change in momentum. I keep at this problem. I see, okay, well, it drives the nail in 1 centimeter into the board. Oh no, that isn't time, right? That is a distance. Assume constant acceleration. Oh no, we have to deal with acceleration now. This is a disaster, except for you know how to do this. This is just using your kinematic equations, right? Where you know that delta x, the distance you travel horizontally, is equal to your initial velocity times time plus 1/2 the acceleration times time squared, right? This is useful because this applies for acceleration. Now, this particular equation, not as useful because you don't have acceleration, you don't have time, too many unknowns. So you look through your other kinematic equations. You will find a kinematic equation that will allow you to solve for time. So you use constant acceleration, kinematic equation, to find time. And then once you have time, earlier we talked about that you can find your momenta. This leaves us with an equation where we just have to solve for our average force by taking our change in momentum, dividing by time. And again, I'm going to leave this to you to finish, but this is the process of solving this particular problem. But thinking more abstractly, the important takeaway here is exactly that connection between impulse and momentum. We think about it like this. Momentum, that is a description of your motion. And impulse, that is a description of your interaction. And we know an interaction causes a change in motion. That is to say, an impulse causes a change in momentum. And that's the main thing that you want to take away from this. That's what you want to think about. That impulse is your change in momentum. Okay, again, I'm going to leave this for you to solve at home. But if you have any questions, feel free to ask. I'm going to do my best to get back to you. And I will see you guys later. Have a wonderful day.